Okay, in this video I want to talk about three infinite series. And there's infinite series that are equal to particular functions that we have looked at before. So these series are series that extend infinitely. They don't stop after 4 or 5 terms. They go on forever and ever. So we'll look at the first one here. We've got a series for e to the power of x. E to the power of x equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x power 4 over 4 factorial, and so on. As my ellipsis saying, go on forever and ever. So these are known as McLaurin series, named after a Scottish mathematician, Colin McLaurin, from the 18th century, who developed work by an English mathematician called Brooke Taylor, also from the 18th century, I think. So this is the McLaurin series for e to the power of x. This is the McLaurin series for sine of x, and this is the McLaurin series for cosine of x. And they're all true, but let's just investigate what they mean, right? So what do they mean? Key thing to remember is they are infinite. These go on forever and ever and ever. So e to the power of x is always equal to this. If we just think about, a very basic number for x, let's think about 0 in each case. E to the power of 0 would be 1 plus 0 plus 0 squared over 2 factorial plus 0 cubed over 3 factorial plus 0 to the power of 4 over 4 factorial, etc., etc. All those subsequent terms after 1 become zeros. So we just get e to the power of 0 equals 1, which we knew already because we know from our work for many years that any kind of non-zero real number raised to the power of 0 is 1. Okay, if we take a sine of 0, let's just look at sine of 0 using my series. Sine of 0, well, that'll be equal to 0 minus 0 cubed over 3 factorial plus 0 to the power of 5 over 5 factorial minus 0 to the power of 7 over 7 factorial plus 0 to the power of 9 over 9 factorial. Let's actually write that in. 0 minus 0 cubed over 3 factorial plus 0 to the power of 5 over 5 factorial minus 0 to the power of 7 over 7 factorial, etc. But I'm hoping you can see that that is 0. And again, that should be no surprise because previous work done in trigonometry told us that sine of 0 is, of course, 0. If I look at cosine of 0, I get 1 minus 0 squared over 2 factorial. If x is 0, we're just replacing all our x's with zeros, plus 0 to the power of 4 over 4 factorial, minus 0 to the power of 6 over 6 factorial, etc., etc. And you'll see again that's 1. And that should come as no surprise because we know from previous work in trigonometry that the cosine of 0 is also 1. Okay, so they're zeros. Zeros, that's what they are. Fairly straightforward. So these series, the key detail is always true. No matter what value of x, this should be true. So if we think about e to the power of 1, let's say. So let me just think about writing this for e to the power of 1. Using my first series here, my McLaurin series for e to the power of x, what we would get is 1 plus 1. 1 plus x is 1 plus x squared, would that be 1 squared over 2 factorial plus 1 cubed over 3 factorial plus 1 to the power of 4 over 4 factorial plus 1 to the power of 5 over 5 factorial, and so on forever and ever. Okay? Now, one thing we know already about e, and again I'm just trying to show you that what this series means, is your calculator can find an actual value for e. It's programmed in there. It's about 2.718281828. That's rounded to 9 decimal places, which is what your calculator will do. It rounds it off. Those decimals, of course, go on forever and ever and ever. We know that e, non-recurring infinite decimal. But if we take our Maclaurin series and we just start to look at each term, if we just take the first term, which is 1 and equals 1, the first term is not a very good approximation for e. But if I add in the second term, so adding in 1 there, we get 2, a better approximation for e. Remember, e was about 2.718. If I add in the third term, 1 squared over 2 factorial. Of course, 1 squared is just 1, so we can just think of that 1 over 2 factorial. we get 2.5. Again, a better approximation for e. Again, let's add in the next term. 1 cubed, which is 1 over 3 factorial. Oh, and we were adding that to our previous answer. So we had, I think, 2.5. And then I'm adding 1 cubed over 3 factorial. So I'm getting that. That's 2.6 recurring. Again, a much better approximation for e. But let's go again to the next term, 1 to the power of 4. So I'm going to add 1 to the power of 4, which is just 1 over 4 factorial. Now we've got 2.7. This is getting pretty close. That's correct. That's a correct approximation of e to 1 decimal place. If I add in the next term, adding in 1 over 5 factorial, again, we get a better approximation, 2.71. That's correct now to 2 decimal places. And again, you could go on forever and ever doing this. 1 over 6 factorial. Add it on will give me this number, 2.718. That's correct now to 3 decimal places. And I'm hoping you can see that these, you just plug in your value for x, and these series get closer and closer the further you go along to the number on the left-hand side. In this case, we're getting, as we go through, we've gone up to 1 to the power of 6 over 6 factorial. We're correct at 3 decimal places. So if we went on forever and ever and ever and ever, this would be perfect. Of course, that's not possible to go on forever and ever, but the series, the sum to infinity of this series is e to the power of 1 in this case, because of choosing x as a power of 1. Let's think about something like sine of pi. And we should know from previous work that we've done in trigonometry what sine of pi is. If you don't, you can check it in your calculator, but you should know that it's 0. I'm going to just check it in my calculator. Sine of pi, I have to make sure I'm in radians here, of course. Sine of pi is 0. So for these series with sine and cosine, maybe I should have started with that, is we have to make sure that we're in radians. So x is in radians. So if we take our series for sine of pi, well, we're just going to replace all our x's with pi's. This is just sine of pi will be pi minus pi cubed over 3 factorial plus pi to the power of 5 over 5 factorial minus pi to the power of 7 over 7 factorial plus pi to the power of 9 over 9 factorial. That's as far as I'm going to go, but I'm hoping you see that that series can be extended forever and ever. And I'm just going to look at how this subsequent terms get closer and closer to what sine of pi actually is, which is 0. We know it's 0. So again, let's just use our calculator here a little bit. If we just take the first term as an approximation for sine of pi, of course, the first term is pi as a decimal. That's what that looks like rounded off. Not very close to being sine of pi, which we said is 0. But then if we put in our second term, minus pi cubed over 3 factorial, minus pi cubed over 3 factorial, we get this negative 2 point something. Again, a little closer to what sine of pi actually is, which is 0. Let's add in our third term here. Pi power of 5 over 5 factorial. Much closer to 0, 0.524. Again, closer to 0 again. Let's add in our next term, which is minus pi to the power of 7 over 7 factorial, which is negative 0.075. This is correct to 1 decimal place, really. This is correct as a approximation for sine of pi. If we add in one more, let's just add in pi to the power of 9 over 9 factorial. Now we've got that. That's 0.0069. That's 10 to the power of negative 3 means move the decimal 3 to the left and rewrite it. 0.0069. So correct to 2 decimal places now. And again, you see these things will work. So these McLaurin series developed by Colin McLaurin, as I say, Scottish mathematician from the 18th century. They give us nice polynomials to describe certain functions, like e to the power of x, sine of x, cosine of x. You know, try cosine of pi. You know, I'll let you try this yourself. We looked at cosine of 0, but try putting cosine of pi. Look at different values for that in your calculator. So we know that cosine of pi from previous work is -1. So check it out. If you didn't know that, just type in cosine of pi into your calculator. Cosine of pi is -1. But use your series here. You would be saying 1 minus pi squared over 2 factorial plus pi to the power of 4 over 4 factorial minus pi to the power of 6 over 6 factorial plus pi to the power of 8 over 8 factorial. And as you go on through this series, you'll see you get closer and closer to -1, the actual value of cosine of pi. So cosine of x is equal to this series. Of course, we've got to remember it's an infinite series. So that goes on forever and ever and ever. Okay, so good to know those three things. Useful series to know. McLaurin series, Colin McLaurin, 18th century.